We're surrounded by these incredibly complex products, everything from the phone in your hand to the airplanes flying way up in the sky. But have you ever stopped to think about how we make sure all that stuff is safe and reliable before it's even built? Well, the answer is a huge shift, a real revolution that's taking us from old-school physical blueprints into the world of digital bytes.
I mean, seriously, think about that for a second. The stakes are just about as high as they can get. You've got to simulate decades of flight, insane turbulence, every single thing that could possibly go wrong. But doing that with a real multi-million-dollar airplane, that's a massive challenge. So how on earth do the world's top engineers pull it off?
All right, here's how we're going to break it down. First, we're going to look at the old way of doing things and why it's just not cutting it anymore. Then, we'll dive into this new world of virtual testing. We've got an awesome case study on something called the digital twin. We'll look at the hard numbers, and then we'll peek into what's coming next.
For decades, here's how it worked. You built a physical prototype. You'd test it, you'd break it, you'd learn something, and you start all over again. But our products have gotten so much more complex. And this old method, well, it's hitting a major wall.
First thing, it is just painfully slow. I mean, every single time you have a new idea for a design, you have to physically build the thing. You're waiting for parts, you're assembling them, you're setting up the whole test. This back and forth can add months, sometimes even years to a project.
And yeah, all that time costs a ton of money, a lot of it. You're paying for raw materials, crazy expensive machinery, and the expert engineers to put it all together. And you're doing this over and over for different versions. And guess what? Most of them are just going to end up in the scrap heap. It's incredibly expensive.
But maybe the biggest problem is that it's just riskier. Because building physical prototypes is so slow and expensive, you can only make a few of them. And that means a major design flaw might not show up until you're way down the road. And finding a problem that late, that can set off a chain reaction of costly changes and absolutely killer delays. And wow, this image just perfectly captures the scale we're talking about. What you're looking at here is a full-scale fatigue test for an aircraft. That entire rig, all those machines, they are built to mimic the stress of flying for thousands and thousands of hours. It's an incredible piece of engineering, for sure. But it's also the perfect example of just how much time, money, and complexity goes into pure physical testing.
And, the experts totally back this up. The Aberdeen Group nailed it a few years back. As our products get more complicated, mixing mechanics with electronics and software, the old-school pen and paper calculations just can't keep up. The complexity's just off the charts.
Okay, so if the old way is cracking under the pressure of modern design, what's the solution? It's a total shift in how we think about this stuff, a brand new approach where we take the entire testing process out of the physical workshop and put it inside the computer.
And this is the key idea right here, virtual prototyping. Basically, you build a perfect digital copy of your product that's based on real-world physics. Now, this isn't just some 3D picture. It behaves exactly like the real thing. You can stretch it, heat it, put it under stress, and run it through millions of different tests, all inside a simulation.
And when you put them side by side, the difference is just night and day. With a physical prototype, you're pretty much stuck with one design. It's slow, it's expensive, and you usually find problems way too late. But with a virtual one, you can test tons of different versions almost instantly, for barely any cost, and you catch those errors right at the very beginning. It's a total game changer.
So this all sounds great in theory, right? But what does it actually look like when it's put to work in the real world? Let's jump into this really cool case study from Mitsubishi Heavy Industries and see how they use this idea to create something called a digital twin.
So this is the traditional way you develop an airplane. It's like a pyramid. You start by testing small materials, then you move up to bigger components, then even larger sections of the plane. And it all builds up to that one single point at the top, the massive, super high stakes, full-scale physical test. Literally everything is riding on that one test going perfectly.
But check this out. Mitsubishi added a whole new, revolutionary layer to this. They built a digital twin. So while their physical testing machine was running, a perfect mathematical copy, the digital twin, was running right alongside it in a computer. And here's the key. The real machine and the virtual one are talking to each other constantly.
And this is where the magic happens. The digital twin gets the exact same commands as the real machine, and it predicts what should happen. Then, it compares its prediction to what the sensors on the physical test are actually measuring. It's on the lookout for tiny differences, little errors that are totally invisible to a person, but are the very first warning signs that a failure is coming down the line.
And boom, here's the proof it works.
On this graph, the system suddenly flags a tiny abnormality. They stopped the test, went to check it out, and what did they find? A single connector had come a little bit loose. Now that's a small issue, but it could have completely ruined the test, causing days, maybe weeks of delays. The digital twin caught it before it ever became a real problem. That one save is pretty incredible, right? But that's just a single example. When you start using this virtual first approach across the whole design process, the data really starts to show just how powerful this revolution is.
Just take a look at these numbers. Companies that use virtual prototyping cut their overall development time by an average of 13%. They also see about 6% fewer change orders after the product is released, which is huge. It means they're getting the design right the first time and avoiding those super expensive fixes after it's already out in the world.
Okay, now get ready for this number. It's absolutely mind-blowing. Dassault Aviation, they developed a whole business jet, the Falcon 7X, completely on a virtual platform, no physical prototypes at all. And the result? They cut their assembly time in half, 50%. That's just what's possible when you go all in on a digital approach.
This chart just lays it out so clearly. The gray line, that's the old way. A failure happens and everything just stops for a long time while you fix it. But the blue line, that's the new way with the digital twin. It detects a sign of a problem early, you take a quick action to fix it, and the test just keeps on going with almost zero interruption. You're basically switching from reactive repair to proactive prevention.
And if we circle back to our case study, Mitsubishi figured that their digital twin system cut down the entire full-scale test process by almost 10%. On a project where every single day is critical, that is a massive, massive win.
So we've gone from physical to virtual, and the benefits are obvious. But this revolution is not over, not by a long shot. The next frontier is all about making these virtual tests not just faster and cheaper, but mathematically provable and even smarter.
And this is where a concept called formal fault injection comes into play. Think of it like this. You're actually blending hardcore mathematical proofs right into your simulation testing. This creates a common language that both designers and testers can use, and it lets you automate failure analysis right from the get-go. So you're not just hoping to find random faults, you are formally proving that the system is safe. You're building a rock-solid, verifiable framework for safety.
So, what's the big takeaway here? We live in a world where things are just getting more and more complex. Our cars, our homes, our devices, they're all becoming smarter and more connected every day. So the question this whole revolution really leaves us with is a pretty simple one. As the products we create get smarter, doesn't it just make sense that our methods for testing them have to get smarter too?